Hello to everybody. I would like to introduce you to our last tutorial for today. This tutorial will be delivered by Professor Piotr Imlik from MIT. The tutorial deals with basically fast algorithms for computing the FFT transform, the FFT in the case of sparse signal. So it's a very, very interesting topic of high relevance. As you may know, FFT was actually seen as the workhorse of electrical engineering and computer engineering for the past 50 years. And in terms of short biography for Piotr, it's sufficient to say that Piotr is one, as well as Professors Sanjeev Arora. Both of them are have been awarded with the Simons Investigator Award. And this award, I mean, if I tell you that last year Terence Tao was one of the awardees, and the award is not given to more than 12 people per year, that actually gives us the exact dimension of the speakers that we have today. And without adding anything, I will let the floor to Piotr. So we have problems with the mic and the fans. Hopefully we'll keep on both of them at some point. If we'll have interferences, we're going to have to shut down one of the two. So Piotr, we have the floor.
Okay, thank you. Thanks a lot for a very nice introduction. And thank you for organizers for inviting me here and for giving this hat. So I actually used to own a hat. I got one when I was on sabbatical in a rich Baranius group in 2009. Unfortunately, I lost it on the plane, so I got a new one now. So, thank you. All right, so let me start by introducing the topic of today's lecture. Today I would like to give you an overview of the work that several people, including myself, have been doing on the faster algorithms, on the topic of faster algorithms for fast Fourier transform. What is the Fourier transform, first of all? Well, I guess all of us here in the room probably know this notion, right? But just to recap very briefly, Fourier transform, or a discrete Fourier transform in this case, is a way to transform data which is sent from the time domain right into data in the frequency domain. Right, so this is typically what you require when you sample your signal, right? Some uniformly sampled time signal. And but if you look at just this signal in the time domain, you don't necessarily get that much information about it. Often, to learn something about it, you transform it to frequency domain, and then you can see, lots of interesting stuff. Right? For example, in this case, you can see that most of the energy is focused in this band. Right? Beyond certain frequency, the amplitude just goes down, and most of the information or most of the energy is just captured by a rather small number. Okay. So this is the fast Fourier transform. This is the Fourier transform pictorially. Formally, we are given. We'll be talking about the discrete Fourier transform, right? So we are given a signal x, right, which is n samples in the time domain. And what you want is to compute representing the Fourier domain, right? So you want to compute the vector, which will denote by x prime. Where x prime is defined using this very well-known formula. And I'll mostly switch between Fourier transform and the inverse Fourier transform without paying much attention, right? Because they are very similar to each other. All right, so that's the Fourier, or that's the discrete Fourier transform problem. And of course, the reason why we are discussing it is because it's incredibly useful, right? Just out of curiosity, how many people used discrete Fourier transform at some point in your lives? Well, I guess it's electrical engineering department, right? Right, but the fascinating thing is that even if if I ask this question in like the science department or other departments, people also raise their hands because it's just very useful. Right, it's very useful for data processing. These are just samples of the applications, and it's also a very useful computational tool. Right, if you have FFT, you can do convolution very quickly. If you have a convolution, you can multiply two numbers very quickly. Right, if the numbers are odd. That's very useful in cryptography and many other applications. Right, so this is really, Fourier transform is really discrete Fourier transform is really the workhorse of not only signal processing but algorithms and other fields. So for this reason, we would like to solve it as efficiently as possible. So all of you know that the fastest to date algorithm for solving the discrete Fourier transform is FFT. And it was invented in the 60s by Kulen-Taki, but the history goes even further, back to even to Gauss. But the most important thing about this algorithm is that it performs this computation in n log n time. Right. So if you just naively perform this operations following from the definition, it will take n squared time. But this algorithm does the job in n log n time, and it really makes possible many applications to make it easy. So it would be great to improve it. Okay, unfortunately, people have been trying over the last probably 40 years, maybe close to 50, and so far pretty much nothing better is known. In fact, the only thing that we know is that some techniques probably cannot be used to prove impossibility of doing something in n log n time. Okay, so we know that certain lower bounds techniques probably do not work. Okay, and even that was interesting. So there has been not much progress on that in that general case. However, what has been known for quite some time is that one can actually perform this task much faster if we assume something extra about the data, right? And in particular, if we assume that spectrum of the signal that we want to compute the Fourier transform of is sparse, or approximately sparse. Okay, so I will define this notion of dominant frequencies and the sparsity in a moment. For now, it's probably simplest to just think about the exact sparsity, right? So in this case, this is how the spectrum would look like. Right, we have k non-zero entries, and everything else is 0. But of course, you don't see this, right? Because this is the frequency domain. This is what you want to compute. So instead, you see your original signal, okay? And what you want is to compute this, right? So this is the output. Okay. And it's probably good to mention that, good to point out is that you do not know in advance where these peaks are located. Okay, so you know there are k of them, but you don't know where they are, you don't know the amplitudes. Right? So the only information you have is the sparsity of the output. So in this case, you can hope for algorithms which are faster than n log n, right? Because they are special inputs. And indeed, it turns out that people were able to come up with such algorithms. The first algorithms of this type were developed for the Hadamard transform, right, which was the Fourier transform over the Boulenger group in late 80s, early 90s by Goldreich-Levy, Kuchet-Mansur, and others. But then shortly, those techniques have been extended, and new techniques have been developed to develop algorithms which are more efficient than fast Fourier transform, even for the standard complex Fourier transform. Okay, so starting from 92, people have been working a lot on developing faster algorithms for the standard discrete Fourier transform. And there has been a lot of work on that. And perhaps the fastest, or the culmination of this line of research, resulted in an algorithm with a running time, which is of the form k times log of n to some constant c. Okay, so we often, in theoretical computer science, we often refer to this as a k polylog of n. That's a log to some power. And this is due to Gilbert multiplication strokes. Okay, so so that's an algorithm which is actually very fast if k is small, right? And in particular, if well, there are some certain assumptions, right? You recall, to get this running time, you have to assume that something called precision, right? But that's a pretty natural assumption, so I'm gonna ignore it for now. If this assumption is not satisfied, then you have slightly slower algorithm, but it's more or less the same ballpark. Now, the interesting thing about this algorithm, or this result, is that it is actually faster than FFT, as long as the ratio of n to k is at least some polylog of n. Right? So as long as k is smaller than n over polylog, right, for some the power of the logarithm, then this running time is faster than the log. Right? Basically, the question is, how many logs we need to go down in order for this being smaller than this. All right, so that was the state of the art when we started to work on this algorithm, on this problem. So, so this is a pretty efficient algorithm. So, what is there to do, right? Oh, by the way, I should have mentioned if there are any questions, just feel free to raise your hand or wave your hands or yes. Okay.
So, in which cases do we know, like a priori, that the signal or the Fourier is k-sparse?
Right. So, I'm using this notion of k-sparsity for simplicity, right? In practice, you see the exact k-sparsity rather rarely. More frequently, what you see is approximate sparsity, which I'm going to define formally in a moment, but roughly speaking, it means that there are a few peaks plus some diagonals. Yes, and that situation occurs quite often, right? In fact, in all of these applications I mentioned, audio, video, medical imaging, and astronomy, you actually see that if you represent your data in a frequency domain, then the data has a there are various ways of calling it. One way is compressible, right? That most of the information is captured in the head of the signal of k coefficients, right? So that situation occurs very frequently, right? And the algorithms will also work for that case.
So one more question. But still, even in these cases, I wouldn't know k, so it seems that I should run for like k equals 1 and then k equals 2.
Right. So k really, the knowledge of k really comes from it's a domain knowledge,
okay,
right? So that's a parameter that you have to have. Sometimes it's given by fiat, right? So for example, in video audio compression, you can say, okay, I just want to keep top 10% of the coefficients because that's how much I can store, right? And that's basically given, right? And then you just leave with whatever tail you get, right? And actually 10%, top 10% coefficients for video actually preserves the video pretty well, right? Not necessarily for images, but for video it actually works pretty well. Yeah. So in some situations, k, is just naturally given to you. In other situations, you have to use your background knowledge, right? And I should mention that a very similar issue pops up also related area of compressive sensing, right? What is k, right? Some algorithms require. Okay, very good question. All right, so that's the that's roughly the state of the art. Okay. So what is there to do, right? I mean, this algorithm, is pretty efficient. Well, so the problem with this algorithm, and in fact with other algorithms, is that although the formula itself looks very nice, once you start actually counting the total number of units of time, right? Once you start doing a more quantitative analysis of the runtime, then unfortunately it's the result is not so great, right? So this is the runtime. So of course the runtime depends on the parameter c, right? And the c is actually something like 4, right? It actually varies depending on which component one uses, but 4 is it's like a pretty much the right answer. And this is the problem, right? Because ideally, we would like to use this algorithm when n is large, right? Because that's where n log n becomes infeasible. So let's say that n is 1,000, right? And then log n is 10, right? Which means that 10 to the power of 4 is actually 10,000, right? So this is actually something which is non-negligible at all. And moreover, the algorithm itself is certainly more complicated than FFT, right? So the big O factor is also present. So all in all, after if you look at the timing experiments which were done by these authors as well as Mark Iwen and other people, the conclusion is that even for large signals, you beat FFTW, which is a very good implementation of FFT, only for sparsity up to like 100 or 200. Okay, so this algorithm works. Okay, and for low sparsity, it actually improves FFT considerably, but it improves only for k, which is small, right? And there are applications which involve sparsity which is that low. In fact, we're going to see examples later. But in most applications, you need sparsity which is higher, right? In order to be effective. So that's exactly what we wanted to focus on when we started working on these problems a few years back. And our goals were twofold. The first goal was in theory, right? We'd like to improve over FFT for all values of k, right? For all values of sparsity. Right? So not only for sparsity, up to n over polylog of n, but we'd like to have a sweet, like a nice statement that we'd like to improve over FFT for all values of k. Right? So as long as k is smaller than n, we would like to have something that runs faster than n. And we also wanted, to have practical algorithms, right? So that one can go beyond, this low threshold and still improve over FFT. So that's the goal. So let's see. So let me. So basically, the rest of this tutorial, I will just give you an overview of how far we managed to go towards accomplishing this goal. Okay. So before I start to describe the results we got, let me first make maybe an overview of what types of the algorithms we are developing, right? So, so first of all of the algorithms that we develop are randomized. Okay, there are some deterministic algorithms, but all the algorithms we see in this talk are randomized or average case, but let's not get into that. The algorithms have a constant probability of success, which is controllable, and we also assume that n is a power of 2. Okay. Now, we don't actually need to make assumptions that n is a power of 2. Some weaker assumptions suffice. But not all of the algorithms work for arbitrary value of n. Okay, so from this perspective, it makes sense to make the simple assumption, which is often satisfying in practice. Now, a few words about this assumption. So we assume that the algorithms are randomized. Randomized means that the randomness is generated by the algorithm itself. Okay, so we don't, except for one specific case that I'll be very specific about. In general, we don't assume that input is random. Okay, we assume that the input is arbitrary, although spectrum in this case sparse, right? But other than that, the values are arbitrary, and we allow the algorithm to toss coins. Right? So the algorithm makes random decisions, and you will see what these decisions are. And because of those decisions, the outcome of the running time of the algorithm can be non-deterministic. Okay. So again, we don't assume anything about the input. Okay. So input is worst case. Okay. So that's the type of algorithms we are getting. And so let's see what kind of guarantees we get, or to be more precise, alternatively, what kind of assumptions about the input we make. So as I mentioned, the simplest assumption is that the spectrum of the signal is exactly k-sparse. Right? So this is exactly what I drew earlier. Right? There are at most k non-zero probability of the output. So the signal is a combination of k pure frequencies. Right? We just have to figure out what they are and what the values are. A more general situation, which I refer to as approximately case-first case, is where we do not assume anything about the input, okay, or about the output, but our goal is to find essentially the top k frequencies, okay, that contribute to the signal. Okay, so formally we utilize the so-called L2 guarantee, which is very popular in sparse recovery and competitive sensing and other fields. And the guarantee, actually, let me ask a question. How many people have seen L2 guarantee before? Okay, so sparse set of. Oh, it's okay. So let me just spend maybe 2 minutes on it. So the guarantee that we get is that if this is the spectrum of our signal, and this is our approximation, okay, then the approximation error, right, the norm of the difference between the truth and our approximation is at most some constant times the smallest possible error achievable when you approximate your signal by a case-sparse vector. Okay, so this formula here, okay, except for C, is really a complicated way of saying that this is the norm of all but k largest frequencies of your signal. Okay. In other words, this is the tail, right? If you take your spectrum and if you remove the top k coefficients, okay, this is the norm of what you still get. Okay. So this is the error that you always have to introduce if you approximate your signal using k coefficients, right? So what we get is something which is within some small constant, and this constant is negotiable. It is within a constant factor away from this object, right? So this means that this algorithm actually, this notion is well defined for any signal. It's just if your signal is a white noise, then the tail is large, right? Which means that your, this thing here is large, so so the guarantee becomes meaningless, right? On the other hand, if your signal consists of exactly k non-zero frequencies, then this is 0, right? Because you can approximate case-sparse signal by case-sparse signal exactly. This is 0, so then this error is 0, and then it means that you have to find exactly the right signal. Okay. So that's the notion that we are going to use, as well as this one. And the third notion, which is very similar to that, except that on the left-hand side you have an infinity norm, right, which essentially means that you bound each coordinate, not just the sum of all coordinates, and you bound it by something which is slightly smaller than this. Okay, so in fact, it can be shown that this implies this. Okay. If this one is confusing, then just ignore it, because it's not really that important. These two guarantees are, the ones that are most important for us. Okay, so this has to be like the most confusing slide of the talk. So, are there any questions about the guarantee? Yes.
So, what do you mean by guarantee here?
By what?
By guarantee.
What I mean by guarantees, well, so yeah, I guess in the exactly case-sparse case, we report this signal exactly. Okay, so I didn't write it here, but that's what I mean by guarantee. In the other case, in the situation where the signal is arbitrary, then we guarantee that what we report, this y prime, satisfies this guarantee. Does it make sense?
Yeah, I think so.
Okay. Yeah, I think that the slide could have been maybe more clear, right? Yeah. But does the notion of a L2 guarantee make sense? Yes.
So in this, do you show there exists a C, or can you actually characterize it?
I can characterize it. Yeah. So you can think about C being say 2. Okay. And in fact, it can be arbitrarily close to 1. But then there's a trade-off between C and the number and the complexity of the algorithm. Alright, good. So basically, that's these are the I would say the properties of the algorithm. So it's randomized, constant probability of success, and it's a power of 2, and we'll mostly consider either exactly recovering k-sparse signal or recovering y prime, right, which satisfies this guarantee. All right, so after this introduction, let me give you an overview of the results we got over the last few years. So somebody told me that every time I give a talk, it has a big table in it. And this talk is not an exception, so here is the table. Actually, it's only a part of the table. But I think that this table really nicely describes the property of the algorithm, and I really like tables. So here is one. Okay, so what you see in this table is algorithms, right? Each algorithm is a row. This is the list of authors. And in each row, in each column, it corresponds to the bound or guarantee of this algorithm. Okay, so for example, this algorithm has this running time, this guarantee, and it has some other properties specified here. All right, so the first algorithm we got on this round had the running time, which was it kind of looks a little bit strange in the context of these other algorithms, right? It was roughly n times k to the power of √2 times some log. So it was not necessarily, certainly wasn't, the running time wasn't k per log n, right? It was, in fact, for many values of k, it was well done there. However, the nice thing about this algorithm, it starts to behave very nicely where k comes close to n. Okay, in particular, it improved over FFT for k almost all the way up to n. I think like up to n over log n. Okay, and this translated into empirical findings. Namely, we implemented this algorithm, and we observed that this algorithm is faster than FFTW for sparsity up to 2,000. Okay, of course, 2,000 is still far from the signal length, but this is an order of magnitude higher than the previous algorithm. Okay, and this was not necessarily due to better running time, but due to lower complexity. So soon after that, we have developed two types of algorithms, right? One for the exact sparsity and one for approximate sparsity with the L12 guarantee. And these algorithms were even faster, not even faster than this one. Okay, so in particular, this algorithm for the exact sparsity runs in time k times log n. Okay, so k times log n has this property that we're looking for, which is that it's always faster than FFT for any k which is smaller log n. Okay, so this is at least in terms of the bound, it is a strict improvement over FFT for all sub-infinite sparsities. And in fact, we implemented the variant of this algorithm, and the variant of this algorithm turns out to be faster than FFTW for all k up to essentially close to 100,000. Okay. So this is this is a range of sparsities that you can actually start doing things. It's a few percent sparsity. Now the caveat is that this improvement holds for the signals which are exactly sparse. Okay, and so since most of the applications involve signals which are not exactly sparse, right? There's always some noise. That limits the number of applications that you can use standard code. But it definitely demonstrates that you can push this line of research quite far. We also developed a variant of this algorithm for the arbitrary signals, right? So this L2 guarantee. And the runtime of this algorithm is pretty much the same as this one, except that there is an extra factor of log of n over k. Okay. The algorithm is slower by a logarithmic factor, but still it has this nice property that this is always better than n log n for any sub-infinite k, right? Because as k goes close to n, and this factor disappears, and then you have only this one. So this was like the first set of results that we managed to obtain. In the next set of results, Okay, we refocused our effort, and instead of trying to optimize the time, okay, or in addition to trying to optimize the time, we also looked at optimizing another important parameter of this algorithm, which is the number of samples that they are taking. Right? So in many situations, you don't necessarily care as much about the time, computational time, but the number of samples that you need to take. Right? For example, if you are in an NMR machine, right? The time you have to spend this machine depends on the number of samples this machine has to take of your body. Right? So if you can reduce that, then even better. So unfortunately, these algorithms here had the running time, had the number of samples, which was basically proportional to the running time. Okay, which was good, but it's certainly not optimal. So the more recent set of results enabled us to essentially match the lower bound. Okay, so we have developed two classes of algorithms. One with a certain set of assumptions, and I will describe this algorithm later, so I'm going to skip these assumptions right now. But if those assumptions are satisfied, then the number of samples for the exact case is order of k, which is optimal. And the number of samples for the general case is k log n, which is also okay. So if this assumption is satisfied, then we are getting algorithms with optimal sample complexity, and also very efficient running. Now these are important assumptions. Okay, we are assuming the average case, and we also assume upper bound dispersion. Okay, so this is certainly not free, right? But if this assumption is satisfied, you are getting very simple efficient algorithms. And more recently, actually very recently, this is still a result which is accepted but not published, right, because the conference will be in January 2014. We managed to get basically a worst case variant of this algorithms, which also are very time efficient, and sample complexity is almost k log n. It's not quite, right? This is log to some power. Okay, we think that we can get rid of this log, but that's still work in progress. Okay. So the bottom line is that in the second line of results, we managed to keep the runtime more or less unchanged, and reduce the sampling complexity, either to optimal or optimal. All right, so that's an overview of the results. Now, I won't be able to talk about all of these things. So the plan is over the next for this first part and the second part is to go over this algorithm and this algorithm. Okay, and part of the reason is because this algorithm uses techniques which also can be used here and here, right? So many of the techniques are shared between this algorithm, and this algorithm is particularly promising, if this assumption is satisfied, because it's a really simple algorithm, and actually a variant of it has been independently developed by Var and Ramchandran, right? And they also showed did lots of experiments, and it really looks like something that works very efficiently, as long as this assumption is satisfied. So we'll talk about this. Yes, questions?
I want to ask about Ramchandran's algorithm, how it compares. I remember it was a k log k in the time, but I wasn't sure about the rest of the.
Which algorithm?
Pawar's and Ramchandran.
Oh, Pawar's and Ramchandran. Yeah. So the algorithms of Pawar. So I have a more detailed comparison later in the slides. But the runtime, I mean, the bounds are essentially the same. In there, we focus on the two-dimensional case, which is isomorphic to the one-dimensional case that they consider, right? And they have a really nice analysis, right? Which actually is not stronger. On the other hand, we handle this case with noise, right? Which they are not handicaps. Yeah. So there is lots of connections, and I'm going to get to that in an hour. Yes.
Could you explain what is the sample?
The sample complexity.
I mean, what is it for a single sample?
I cannot hear you.
So you mean you said if you need k samples, then
right?
Does it mean
order of k samples? It means that you only need to sample the signal. Second.
Out of n values?
Out of n, you only need order of k. Yes. Any other questions here?
What is average constraint in terms of where you need to take those K samples?
That's again?
You said you only need to have K samples, right?
Yes.
Is there any concern about where you need to take those K samples?
So I have to take them where the algorithm tells me to. Yeah. So these are not arbitrary samples. Yeah. The algorithm, says I want this, and this. Yeah. My question?
What is average case?
I'm gonna define it in the next. All right. So I think I started like 5 minutes after 3, or
Yeah, so would like to continue, or you can make the break now, it's up to you.
I see.
Would you like to make the break now or continue another 5 minutes, it's up to you.
Oh, I see. I can go for another 5 minutes.
Oh, whatever.
10 minutes.
Yeah, 10 minutes is fine, yeah.
Okay. So I go for another 10 minutes and then we'll
Have the break.
All right. So that's the basically plan of the rest of the stuff. Right. We're going to see an overview of how this algorithm works, and we're going to see how this algorithm works. And if time allows, I'll also go over a few applications and future directions. Okay. All right. So this is our goal for the next few minutes. Right. So we assume that the signal is exactly, the spectrum is exactly K-sparse, and want to get this rank. So here is the intuition behind the algorithm in just one slide. Okay, so we'll get this algorithm as a sequence of steps. And the last step is what we actually do, but it's good to see, how essentially FFT morphs into our algorithm. Okay, so this is what you get, if you apply FFT. Right, this is your signal time domain. You apply FFT, you get this thing here. Right, and the problems that arise in time and local. Okay, and this is despite the fact that most of the things in the output are zeros. Right, so you really don't have to output them, but FFT computes all of these things even they are zeros. So ideally, you would like to reduce the running time. You have to reduce the input size and the output size. Okay, so the first step towards our algorithm would be to just take the signal, but only keep the prefix of it, and zero out everything else. Okay, and then you run your FFT on this, and you get something that looks like this. Okay, so what it means from the harmonic analysis perspective. Well, one way of thinking about it is that you multiply your signal by a boxcar filter coordinate-wise, right? So that's zero out everything except for the first few coordinates. And the frequency domain, this corresponds to convolution with the Fourier transform of the boxcar, right? Which is the sinc, right? So basically, what you get is you are going to get the sinc around every peak. Okay, that's what you get. So in a way, we reduce the size of the input, right? But really, nominally, still the length is n, although there are many zeros here. So what we really need to do is we need to reduce it further. And basically, what we do is we take the signal and just wrap it or alias it right around the subprefix, which basically means that we really only keep the first B samples. Right, and the signal itself is of length p, not as n, not n as here. So in the frequency domain, aliasing here corresponds to subsampling, right? So what this computes, okay, what happens if you apply FFT on this signal is we get basically samples of the signal, right? So we get this signal in blue, which approximates the original this signal appears here in green. So that's what our algorithm does, okay? And then the main thing which is left is to figure out how to go from this to this, okay? So you can see that this signal, resembles these signals pretty well, right? You have peaks here, 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 right? So we also have, the slight samples here, here. But, of course, there are many issues, right? So overcoming those issues, right, figuring out how to go from here to here is basically the main part of the algorithm. Okay, but in a nutshell, this is all that the algorithm does.
The frequencies are changing.
Well, we assume the frequencies are constant. Yeah, that's stationary.
Because something is maybe induced by transient. I mean, you pick up the first part,
Right.
but whatever happens that is of interest is much later in the.
Right.
So, and therefore those are the frequencies that might be of interest. So,
Right.
the fact that you're picking up the first window, you
Right.
might completely neglect what's happening in the rest of the signal. So.
Yes, and in fact, so this is one of the problems, and we are going to see the solution to this problem in a moment, right? Yeah, so really we are not going to pick up the first few, right? But this is really the main idea, the main outline of the algorithm actually. So what are the problems? So certainly what you mentioned is one problem, that if you just look at the prefix, it doesn't tell you everything about the signal, right? And there are ways of describing this issue, from the harmonic, when you look at the spectrum perspective, right? So here are, some of the issues, right? One issue could be is that two non-zero coefficients can be very close to each other, right? And in this case, if you put the sink around, both of the strings, then the sinks overlap, right? And then when you look at this thing here, you just don't see whether there's one sink or several, right? So this is one issue. The second issue is leakage, right? So even though these frequencies here are well separated, still, the value of this frequency influences the value of this sample and vice versa, right? Because the sink, it goes, it decays as 1/x², the amplitude of, it basically decays polynomially, which means that even here you see some influence of the stuff, right? So that's also not good, because that means that just by looking at this value, you don't know where the value came from, a peak or maybe its neighbor. So this is a second problem. And the third problem is finding where this frequency actually came from. Right, so if you look at this, okay, maybe you know that there is something, some frequency with this amplitude, and so on. But you don't know where they came from, right? Because the resolution here is much smaller than the resolution here. So we can set the three things that one needs to resolve, right? Or these are the three things that one can identify, right? Or some of the things that are to resolve. So let's see how we do it. So the first problem is solved by essentially using a simple trick which was introduced in the earlier work, which essentially lets you assume that the spectrum is permuted pseudo-randomly, right? So you apply a simple trick which lets you assume that these things are in arbitrary places, and this in particular means that with good probability, no two frequencies are too close, right? Because the probability they fall close to each other is very low. Okay, and this is achieved by sampling the signal, not in the way I described here, right? Just take the first few samples, but by permuting the signal in a pseudo-random way, and then taking the first few samples, right? Which means that really the sampling will be done all over the place, right? It's just that we can view it as first permuting the sample in time domain and then taking the premise. Right? So this avoids this problem that leakage will be resolved by replacing the boxcar filter, right, by a nicer function, such that this fall-off will be much faster. Right? So the frequencies are not going to leak too much to each other. And last but not least, in order to find the support, if here we're talking about the exactly sparse case, and then it's particularly simple. Basically, we show how to recover the position from the face. Okay, and by combining these two things, essentially that's the main component in our algorithm. Okay. Any questions right now?
So once you commute the support in the Fourier transform, can you recover
the original ones?
Yeah.
Yes, we can. Yeah. So I'm thinking that maybe it would be a good idea for me to show how to do this. Okay, just to so that you can get some idea of of the side of how to get rid of this, and then after that you can stop and take a break and then continue. Okay, so let me basically describe the first trick, right? So, so as I mentioned, this is the trick from earlier work, which we employ also here. The basic idea is that instead of sampling from the original signal X, we sample from the signal Z, such that the teeth coordinates of that signal is equal to this thing here. Okay, so here you see that T is multiplied by sigma, right? It's taken modulo n, right? So sampling in Z, 1, 2, 3, and so on, corresponds to jumping by sigma, right? Modulo n in the second signal, and there is also a phase shift. Okay. So what does this operation do to the spectrum of the signal, right? So if you look at the spectrum of Z, then it's easy to see that the frequency that falls here is the frequency that was in the original signal at the position which is the inverse of sigma times f plus beta. Okay, so the beta comes from the phase shift, right? Because phase shift in a time domain corresponds to the frequency shift in the frequency domain. And this sigma here comes from subsampling. Right? So you subsample the sigma in time domain, so you subsample by inverse in the frequency domain. Okay? And this is well defined if sigma has an inverse, right? If n is a power of 2, then any odd number has an inverse. Okay? All right, so if we subsample in this way from the time domain, we get the signal with the spectrum. And this is actually very good news, okay? Because in theoretical computer science, what people observe is that if we choose this sigma and beta random, then this way of sampling, it has a so-called pairwise independent property. I'm not going to define exactly what it means, but for all practical purposes, for many situations, this mapping from F to this thing almost looks random. Okay, which means that if we sample from this signal, okay, then it will be as if we were sampling from the original spectrum, signal with the original spectrum, but after a random rearrangement. Okay, and this means that we can pretty much assume that the frequencies are in the random positions. Okay, and we can reap all the benefits from them. For example, the two frequencies do not fall close to each other with high probability. Right? This is impossible. I mean, this has very low probability under a random rearrangement. And there are tools that there are simple proofs that let you show that the same is true, even if you permute your frequency using this way. Right? It's not completely random. It's a random affine function, but still it's random enough to prove one. Okay. And this is really good. After you apply this trick, okay, you can assume that your spectrum is random, and you can use all these properties. And you can also see that whenever you want to access, sample of Z, right, you can simulate it by accessing this, right, and performing multiplication by hash. Right. So for all practical purposes, you can assume that you are sampling that your signal has spectrum like this, and then do the. Does it make sense? Are there any questions? Huh?
So the complexity of this step should be number of samples times log n, right? If we assume like a logarithms as seed for the random generator.
The complexity of each of these steps, you mean of the...
Taking a random number, basically.
Oh, I see. So random number is really something that on modern computers you can do in constant time, right? So that's what we assume. I mean, one can be more clever about it, right? But we just assume that randomness comes from random. Yeah, so this is basically the main source of randomness that we use in this algorithm. This lets us, assume that for all purposes, these coefficients are in random positions, right? Which particularly means that it's unlikely that two of them are really close to each other, or close to each other, which means it's unlikely that this two systems are random. So this is how we solve the first case, the first problem. So I'm gonna stop here, and then after like maybe 5 or 10 minutes break,
10 minutes break.
10 minutes break, we're gonna